Many people dream of living by the sea, but being close doesn't always mean having a view. This building is only a few steps from the beach, yet it will never see the ocean. The problem is not distance, the problem is height.
Cheese Bites!
A building has an ocean view if every building in front of it toward the ocean is strictly shorter. If there is one building that is equal or taller, the view is blocked. That's all. So how do we check this in a systematic way? Suppose we want to know whether a single building has an ocean view. Let's pick the one farthest from the ocean. It has height 4. In front of it, toward the ocean, we see buildings with heights 1, 3, and 2. All of them are shorter. So this building has a view. Now try another one. This building has height 2. In front of it, we see 1 and 3. 3 is taller than 2, so this building is blocked. Just one building that is taller or equal and the view is gone. That works, but what if we want to know which ones have a view? We don't just want to check one, we want to find all of them. We can repeat the same check for every position, then repeat the same process again and again. Let's make this visual. We draw a matrix. Each column is a building. Each row is a comparison with building closer to the ocean. Every time we compare two buildings, we place a dot. The building closest to the ocean compares with no one. The next compares with 1. We compare with the first one, so we place a dot in the first row. Then we move to the next building. Now there are 2 buildings in front of it, so we compare with both of them. That fills 2 rows. Then the next building compares with 3, and this keeps growing. If we call n the number of buildings, then this pattern forms roughly half of an n by n grid. That's why the running time grows quadratically. It works, but it doesn't scale well. Let's try a couple of small examples and see what we can learn. Take 3, 1, 2. The first one is already the tallest, so none of the ones behind it can have a view. The only way something behind can get a view is if it becomes a new record. So if we add a 3, nothing changes. In real life, we might argue it has a view, but in our problem definition, it doesn't. It's still blocked by the first building. If we add a 4 at the end, because 4 beats the maximum so far, it has a view. So here is the idea. As we move away from the ocean, we keep track of the tallest height up to this point. If the current building beats that value, it has a view, and we update the maximum. Let's implement this in Python. First, we prepare a list to store the buildings that have a view. We also keep a variable called max so far. This represents the tallest building we have seen up to this point. We start with a sentinel value of -1, lower than any valid height, so the first building always counts as a new maximum. Now we scan the buildings from left to right. Remember, the ocean is on the left. For each height, we check one condition. Is this building taller than the maximum we have seen so far? If it is, then it has a view. So we record its position, and we update the maximum because this is now the tallest building. At the end, we simply return the result. So the whole problem comes down to a single idea. Keep the maximum height seen so far. Here's something you can try next. What changes if the ocean is on the right instead of the left? And what if there is ocean on both sides? This was today's Cheese Byte. Remember, the code matters, but the idea comes first.